Hi everyone, my name is Bat-Sheva and I will present a paper written by Yaniv, Matteo, Yanfei, and I. Training Uncertainty-Aware Classifiers in Conformalized Deep Learning. The goal of this paper is to introduce a new learning technique that in combination with conformal prediction methods lead to machine learning models with approximate conditional coverage. In order to understand our suggestion, I will give some background on conditional coverage and conformal prediction. So our input is training data and a test point that are sampled IID from some distribution. X is our feature vector, Y are our labels. Our ideal goal would be to use a machine learning model to construct a conditional distribution-free prediction set. This means that the probability of the true label to be included in a prediction set conditioned on xn plus 1 being equal to little x, this probability is greater than or equal to 1 minus alpha, which is our coverage level, for example, 90%. So let's say we have an image, we pass it through some black box. We would want to achieve a prediction set. And we would know that the true label is included in this prediction set with probability that is greater than or equal to 90%. And this property should hold on a specific image. Unfortunately, it's impossible to achieve conditional coverage in finite samples and for any distribution unless we make some strong assumptions. But conformal methods do manage to construct prediction sets with valid marginal coverage. This means that the previous property holds on average for all images. In this talk, I will present a new learning technique that leads to machine learning models that think conditional coverage. So let's say we have an image and we want to produce such prediction sets. How do we do so? We pass it through some neural network and we achieve the estimated conditional probabilities, p hat of y given x. We sort these probabilities and we sum them up until reaching 90% coverage. 90% is our coverage level, which we denote by tau. In this case, our prediction set includes labels 1 and 2. The problem with this naive approach is that it may not achieve the desired coverage. This is because we don't know if our estimated probabilities are close to the real ones. We don't know how good our classifier is. That is why we need conformal calibration. We would want to tune the raw coverage parameter on holdout data. For example, let's say we want to achieve 90% coverage. We compute the actual coverage evaluated on holdout points, and we see that in order to achieve 90% coverage, we need to ask for 95%. That is why for the previous example, we also need to include label number 3 in our calibrated prediction set. How do we find this tau hat? How do we find this calibrated coverage level? So we use holdout set denoted by I calibration, and the core idea is to compute scores and use them to find the calibrated tau. What are these scores? Let's say we have the same image from before. We pass it through some neural network and we achieve the estimated sorted probabilities. We sum these sorted probabilities until reaching the probability of the true label. In this case, the score is equal to 0.95. This is what is written here above and denoted by WI. We do this for all images in our calibration set and compute tau hat, which is the 1 minus alpha empirical quantile of these scores. Finally, our output would be the calibrated prediction set, which we compute as before using this tau hat. These sets achieve valid marginal coverage. So what we do up to now is take an image, pass it through some neural network, and calibrate the results, calibrate the coverage level, and achieve a prediction set with valid marginal coverage. What we suggest to do in our paper is combine these two phases of training and calibration during training and achieve a machine learning model that thinks conditional coverage. How do we do this? We base our suggestion on a theorem mentioned in the paper. For the oracle classifier, pi, which is the perfect model that has access to the true conditional class probabilities, the conditional scores, Wi, conditioned on xi, follow a uniform distribution. Moreover, they are uniform if and only if we achieve valid conditional coverage for any coverage level. So we understand that if we promote the scores to be uniform, we may achieve valid conditional coverage. For example, here we see that for the oracle, that is the perfect model, the scores are uniform, while the scores of a neural network using the regular cross entropy loss, the scores are far from uniform. The question is, how do we drive the model to produce more uniform scores? This is how we do it. We split our training set into two distinct subsets, I training and I calibration. For each subset, we compute a different loss function. For I train, we compute the cross entropy loss, which is the accuracy loss. You're probably all familiar with it. And for I calibration, we compute the new loss function we propose, which is the uniformity loss. It returns the maximum distance between the empirical CDF of the scores to the true CDF of a random uniform variable. Finally, we sum up these losses and take a gradient step. The problem is that this loss function is not differentiable. It involves sorting and ranking, which are non-smooth operations. Therefore, we used a Python package that was published not long ago that allows us to use fast and differentiable sorting and rankings. This loss function drives the scores to be more uniform and promotes conditional coverage. In conclusion, we suggested in our paper a new training algorithm that mitigates overconfidence in deep neural nets. We do this by minimizing a new loss function inspired by advances in conformal inference. In the paper, we presented some experiments that show that our method manages to achieve smaller prediction sets with higher conditional coverage. We conducted experiments on synthetic data and on real data, for example, C410, which you can see here below. For more details, please look at our paper. Thank you.